Hello guys, welcome to the 7th class of this course. In the last class, we talked about the virtual displacement, which is basically the change in the configuration of a system due to the infinitesimal change of its coordinates. It is not actually a displacement is in time. It is not a real displacement. That's why we call it the virtual displacement. Then we talked about the D'Alembert's principle. So which is, I will write it again here. Principle, which is if there are n number of particles and each, I mean, there for the ith particle, the force, the external force on it is FIE, then FIE minus the rate of change of momentum of this ith particle, that is PI dot delta RI, which is the virtual displacement of the ith particle, sum over all particle equal to 0. So let's call it equation 1. So we will need this D'Alembert's principle to derive Lagrange's equations. So there we also showed that this first term of the D'Alembert's principle, so sum over I Fi external dot delta Ri equal to sum over J Q capital Qj times delta small qj, where this delta small qj, these are virtual displacements in generalized coordinate, which are basically independent set of coordinates. And this capital Qj, this is called the generalized force. Generalized force, which is Fi external dot delta Ri delta Qj sum over all I. This is the generalized force. So let's call it equation 2, and this is the expression of generalized force. Let's call it equation 3. So to derive this, we used another equation, which is delta Ri. This is a virtual displacement in the original coordinate, or let's say that in initial set of coordinates. If I transform it in the generalized coordinates, then it will be delta Ri delta Qj del Ri del Qj times delta Qj. And there is no delta Ri delta T term because these are the virtual displacement. So there is no explicit T dependence. So there is no terms like delta Ri delta T, del Ri del T. Ri del Ri has no explicit dependence in time because these are virtual displacement, not actual displacements. So let's call it equation 4. So these are few equations which we used in the last class, and we will need them. in this class. So I just summarized them in the beginning. Now let's look at the second term. So this was the first term. Equation 2 was the first term of this D'Alembert's principle. Now let's look at the second term, which is sum over I, the second term. So this was the first term. This is the second term. Sum over I, Pi dot delta I. This is the second term. I'm not considering the minus sign. When I will write the entire equation 1, then I will consider the minus sign. For the time being, let's consider only this term. So without the minus sign. So what is this Pi dot? This is the rate of change of momentum. So Pi is mi mass times velocity, Ri dot. Velocity means dri dt, that is Ri dot, rate of change of position with respect to time. And so this is Pi, and if we put it, so then Pi dot will be mi Ri double dot. Okay? Double derivative. We are taking derivative both side again. So then this term will be sum over I mi Ri double dot delta. Right. So now this delta Ri, this is the virtual displacement in the original coordinate, but now we will replace it by this equation 4. So then we will get an expression where the delta qj's will be there. So these are the virtual displacements in generalized coordinates, and delta qj's will be independent of each other. That is the advantage we want to get. So let's look at this equation and put it here. So I mi Ri double dot sum over j delta Ri delta qj del Ri del qj times delta qj. Equation 4, using equation 4. Then, so this I and j, these indexes are independent. So we can put j outside, and then it will be so I mi Ri double dot del Ri del qj times delta qj. Okay. So this is the second term. So let's call it equation 5. So now concentrate on only this term. Okay, only this term. So let's call it chi. It will be easier to track then. So then chi equal to so I imam Ri double dot del Ri del Qj. Okay. Now let's calculate another thing. So let's calculate ddt of mi ri dot del ri del Qj. What will be this? This will be, so mi is constant. So uh, this derivative of ri dot, which will be mi ri dot del ri del Qj plus mi ri dot product del ddt of del ri del Qj. Okay. So then now see this term. So this is this inside the summation. This is the term. So then we can write mi ri dot del ri del Qj equal to ddt of mi ri dot del ri del Qj plus sorry minus mi ri dot product ddt of del ri del Qj. Okay. Now let's call it this is equation 5. So let's call it equation 6. Equation 6. So now I will write two equations which will be proven in the next class. Okay. So for the time being, you have to assume that these are correct. So I will write it in the red box. So to be proven in the next class. So the equations are ddt of, so this term ddt of del ri del Qj equal to del vi del Qj. So I will call it equation 7, and another equation is this del ri del Qj is del Ri del Qj del Ri del Qj, which is equal to del Vi del Qj dot. Okay, so let's call it equation 8. So these two equations, I will prove them in the next class. You guys can also try yourself. I will do them in the next class. So this is the VI. VI means velocity. Okay. So VI means dRi dt. It's the definition of VI. So now using these two equations, so using equation 7 and 8 from equation 6, we can write mi ri double dot mi ri double dot del ri del qj equals to del ri del qj equals to ddt of mi ri dot, and in place of del ri del qj we will write this del vi del qj dot. Okay, so ddt of mi ri dot ddt of mi ri dot product del vi del qj dot. Del qj dot means time derivative of qj, dqj dt. Okay, and there is another term, so minus mi ri dot minus mi ri dot and dot product this ddt of del ri del qj. This is from equation 7. This is del vi del qj. Okay, so mi ri dot product of del vi del qj, mi ri dot del vi del qj. Okay, now this ddt of mi, what is ri dot? Ri dot means dri dt, which is basically vi. So this is vi dot del vi del qj dot minus mi. So again this is ri dot, which is vi dot del vi del qj. This means ddt of mi by 2 del qj dot vi square. So if you take the derivative, then a 2 will come and it will cancel the 2 below, and we will get v dot del vi del qj. Okay. Minus mi, again half del qj of vi square. Okay. So as mi is constant, it's independent of qj dot, independent of qj, independent of time. It is a constant. Then basically what we have is ddt of del qj dot half mi vi square minus del qj of half mi vi square. So what is half mi vi square? This is the kinetic energy of ith particle. So what we have is ddt of del qj dot of ti, this is kinetic energy of the ith particle, minus del qj of ti. Okay, so this is this term. So let's call it equation 9. Equation 9. This is equation 9. So now let's put it in this equation, in this expression of chi. So we try to find the expression of chi, and that's why we did these steps. So let's find the expression of chi then. This term, this expression of chi is, so then expression of chi is, then chi is sum over i, sum over i, sum over I mi ri dot del ri del qj, which is basically this term, mi ri dot del ri del qj, mi ri dot del ri del qj, del ri del qj, which is basically this. So this is sum over I ddt of del q j dot of ti minus del q j of ti. Now I can take this summation index over I, summation over I inside, then we will get ddt of del qj dot of sum over I ti minus del qj of sum over I ti. And what is the sum over I ti? What is ti? Ti is the kinetic energy of ith particle. And if we sum over all the particle, then we will get the total kinetic energy of the system, which we will denote by capital T. So ddt of del qj dot of capital T minus del T del qj. Here T is total kinetic energy of the system. So this, let's call it equation 10. Equation 10. So then let's see what we have. So in this equation 5, which is basically the second term in the D'Alembert's principle, this is the second term. So in the second term, it basically becomes like, so from equation 5 and 10, from equation 5 and 10, the second term, which was sum over I pi dot delta I, it becomes, so which was this, which was sum over I pi dot delta I, which becomes this sum over j chi times delta qj. Okay, so sum over j chi times delta qj. This chi has a j index basically. Okay, this chi j, let's call it chi j because it has a free index which is j. Let's call it chi j. I index is summed over, but there is still a free index. So this is chi j. So then, and what is chi j from equation 10? This chi j is this term. So this is sum over j ddt of del t del qj dot minus del t del qj. This is chi j times delta qj. Delta qj is the virtual displacement in generalized coordinate. This is the second term. Let's call it equation 11. Okay. So then, using equation 1, equation 2, so I can, so equation 2 is basically the first term, and equation 11. So using equation 1, 2, and equation 11, what we get is sum over I if external I dot delta Ri is equal to pi dot sum over I dot delta Ri, which is, so from equation 1, this force term, we will write it in terms of generalized force and generalized coordinate, which will become sum over j qj delta qj equals to, so let's write it in the original form. Let's write the minus sign. And this term will be sum over j from equation 11. From equation 11, we are getting this term, second term. This sum over j ddt of del t del qj dot minus del t del qj delta of qj equals to 0. So now I can write like sum over j ddt of del t. So just multiplying it by -1, then a sign change will be here and here will be a sign change. So del t del qj, and this is minus qj delta qj equals to 0. Okay, so let's call it equation 12. So now look at this equation 12. So, and look at equation 1 first. So here we have this delta ri's. So delta ri's are not independent. They are not linearly independent. So in that case, the coefficient of delta, as this expression is 0, sum over I, this some coefficient, and then times delta ri, this is equals to 0. And from there, we cannot write the coefficients are individually 0, because this delta ri's were not linearly independent. But now, look at this term, this equation 12. Here, this delta qi, qj, these are linearly independent, because qj's are generalized coordinate. So they are the minimum number of coordinates required to describe the system, and they are independent. So in that case, the coefficient of this delta qj, which is basically this term, they will be individually 0 for each j. So we can write them. So as delta qj's are linearly independent, then ddt of, so its coefficient, that is ddt of del t del qj dot minus del t del qj minus qj equals to 0. Okay. This is equation. So for all j, this is equation 13. Now let's look at this qj, this generalized force. So what was qj? Qj was sum over I fi external dot del ri del qj. Now if we consider the conservative force field, that is fi external, which is basically which can be derivable from a scalar potential, this is delta iv, is the divergence of the um, scalar potential. So V is the scalar potential. V is scalar potential. So if we assume that these external forces can be derived from a scalar potential, then which basically means it is conservative, then this Qj equals to minus sum over I divergence of V dot delta Ri delta Qj, and which equals to minus of del V del Qj if V has no explicit dependence of Q dot K's and time. Okay. So this is basically the chain rule of derivative. So this is not Q dot K. This is R dot. This is a velocity. Or Ri. Let's say R. Let's write Ri. It's not Q because it's Ri. So it is the simple chain rule. So if V depends on Ri, all Ri dot and T, so then del V del Qj will be sum over all I del V del Ri, which is divergence of EA, which is basically not del V del Ri, which is divergence of U with respect to I coordinate. This is divergence of V del Ri del Qj plus sum over all I del V del Ri dot del Ri dot del Qj plus del V del T times Qj dot. But these terms are not there. So these terms are not there here in this expression. So we in this expression, so we are writing equating this term with this term. So only this term with this term, and this, so only they will they can be equal only if these other terms will be when these other two terms becomes zero. That means this V, it doesn't have any velocity dependence and it doesn't have any explicit time dependence. Okay. These dependencies are not there. 0 and 0. So in that case, so let's call it what was the equation? This is equation. This was equation 13. So let's call it equation 14. So then from equation 13 and 14, what we have is this ddt of del t del qj dot minus del t del qj. So minus qj, and here in the expression of qj there is a minus sign, so it will be plus del V del Qj. Del V del Qj equals to 0. So equation 13 equals to 0. Now we can write like ddt of del T del Qj minus del T del Qj. So let's take this. So V also here, I mean, so we will have like del Qj of T minus V equals to 0. Now we can also write this equation like del T of del Qj dot of T minus V. Wait a second, bracket here. T minus V minus del Qj of T minus V equals to 0 if V has no explicit Qj dot dependence. Then this derivative will eventually be 0. So this term will be equal. We can always write this. So now let's define a new function, which we will call the Lagrangian. Lagrangian, denoted by L, which equals to P minus V. The kinetic energy minus the potential energy. So in that case, this equation will become ddt of del L del Qj dot minus del L del Qj equals to 0. This is called the Lagrangian equation of motion. Or Lagrangian equation of motion, or Lagrangian or Lagrange's equation of motion. So it's a very important equation, and we will use it to solve many problems in this chapter. So in the next lecture, we will derive these two equations first. These two equations, we will derive it. And then we will talk about the uniqueness of this Lagrange's equation. So is it unique? Is the choice of this Lagrangian, is that unique? So it's an easy choice, like kinetic energy minus potential energy. That's a very easy choice. But is the choice unique? Is it the only choice we have? So we will see that this is not the only choice. There can be a undefined number of Lagrangian we can create for a system. So we will talk about them, and we will derive those equations in the next class. Okay, bye.